Hi everyone, welcome back. Okay, now we're going to take a look more closely at macromolecules or polymers. If you were in my previous video, then you will know that I actually posed a question on the ester structures and asked you to put a comment. So now it's my turn to comment back again. So these are the corrected answers, right? So we need to follow back the names. So for example, if you have the first one, ethyl, we have 2 carbons on the alcohol side. Methyl, then you'll be 1 carbon on the other side, right? And then after that, if it is ethyl, then you'll be 2 carbons on the other side. So sorry about the alcohol column. All right. For the ethanoate side, 2 carbon, ethanoate, 2 carbon, methanoate, 1 carbon. All right. And all 3 we have your functional group, like that. Okay. So let me correct this. This should be the like this, and this would be your methyl methanol, like this. All right, now let's take a look at the macromolecules now. All right, actually we are looking at your polymers and macromolecules. Okay, so the definition of the macromolecule is any long chain molecule that contains many atoms, okay, bonded by strong covalent bonds. Okay, so no simple molecular structures anymore. So they are joined by linking your small units known as your monomers. All right, and then this is our definition: joining of a large number of small molecules to form a macromolecule. So we have actually 2 types of polymers: your natural and your synthetic ones. Natural ones are literally found in nature. Your proteins, carbohydrates, and fats are all polymers. Okay, and we're going to study 3 specific synthetic ones. Synthetic means fake, and we can produce them by man. Okay, so there are 2 types of reactions. One is addition and one is condensation, polymerization. Okay, so we're going to take a look at the first one, addition polymerization, where the definition is this: the process of linking your unsaturated monomers, okay, to form your polymer without losing any atom or molecule. All right, so this is a generic condition. It can change depending on what kind of polymer we want. We're going to look at the first simplest one is your polyethylene, which is your plastic bag, right? The one where you eat your seaweed chicken, that is mostly polyethylene, low grade or low density polyethylene, the thin and flimsy one, which is suitable for putting your food items. Okay, flexible and difficult to break. And how is it formed? All right, this is actually our mechanism. So we have our monomers here. Monomers are your starting materials, that means haven't reacted at all. So you can see the double bond, and so on, right? What happens is that one of the double bond will actually break. Okay, and each of the bond actually forms 1 electron here like this, 1 electron here, and that's where you see you can form a new bond like this. This thing here is what we call a repeat unit. It does not really exist in reality, but we just use this to isolate this to tell us how the polymer looks like, 1 block or 1 slice of the polymer looks like. Okay, and that's about it. Okay, so what's the difference between the monomer and the repeat unit? This is the starting unreacted material, unreacted, and this is just like a slice of the product. Okay, that's about it. All right, so we can represent this in many ways. We can use this as a word equation here, or we can use your chemical equation like this, or I think it's simpler for us to simply put it this way in the structural formula. Okay, to look at the drawing, you notice that the position of the end is also different. Here means they are all separated. Here means they are all bonded together already. Okay, so how do we deduce the structural formula of the monomer from the polymer? So for example, there are many ways we can look at it. We can look at it the red one, the blue one that's repeating, or we can even look at it like this. Anyway, as long as it really is repeating. All right, what we're going to do is that we are going to identify one first, any one, and it's very simple. We are just going to simply write down the formula of the repeat unit, convert the single bond into a double bond, and done. we are done. Alright, I want you to notice that, hey, this thing here, it doesn't matter. As long what I want is for addition polymer, I want to arrange it in this manner, in this, whatever I draw, I want to get it in this format, so that if I want to get a repeat unit, I just make it a single bond. If this was a single bond, I just make it a double bond to make it the monomer. Okay, these properties you can read on your own. Alright, and these four things here are actually the things that never change in your addition polymerization. That means your empirical formula, percentage by mass, and products of combustion. No different, because they have the same number of atoms. Alright, so here we have this percentage yield. I think it's very, very easy. If we have 50 tons of ethene but only 30 tons of polyethylene, that means the 20 tons didn't react, so the percentage yield is just 60%, just like that. Alright. Next, the use of addition polymers are like this. Because they are plastics, just think of addition polymers as your plastics. Right, good insulators of heat and electricity, resistant to chemical attack, so your cups and all that. Your polystyrene, which is your, when you tap out the plastic, sometimes you put some hor fun and all that, that's your polystyrene, slightly harder. Teflon, the non-stick property, alright, is also an addition polymer. Some people like it, some people don't like it, because it has a relatively low boiling and melting point. That's why the chlorine and fluorine, all that tends to come out. This thing, perspex, is more interesting. I think we have it, but nobody knows what's that. Alright, actually it is in your screen protector and all that, your tempered glass. Perspex is interesting because it is not that it does not break. Instead of shattering into pieces, it just becomes a spider web. Alright, that's the specific property of perspex that's better than glass in that sense. Okay, now we'll move on to the next one, which is condensation polymerization. Okay, and then this one is slightly different because we have different functional groups reacting now. Alright, and then we have a small molecule, most of the time is water, which is produced as a byproduct. That's the difference. Okay, and this is the definition. Now we have different monomers with different functional groups to form a polymer with the elimination of a simple molecule. Okay, we have two types of condensation polymers that we're going to explore: the polyamides and the polyesters, or polyesters. Okay, polyesters, I think all these you have heard of these names before in your clothes. Alright, so we're going to look at these two, nylon and terylene specifically. Okay, so nylon, right, actually is working by looking at the dicarboxylic acid. Di means got two acids. Diamine means got your this thing here. If you look at the amine, it looks like your ammonia, and it's actually a substituted ammonia. That means one of the H is replaced by a carbon chain, something like that. This box here is just a long carbon chain. Alright, so again, we're going to cut them. Remember I talked about the esters, right? It's like that. We're just going to cut away whatever here. You can cut away until it's left with the C double bond O. Everything else, we cut away only one atom, usually the H. Okay, so what happens is that it will form water, usually, and you will form your peptide or amide linkages. Same concept as your esters. Alright, just that we're going to cut both sides of the molecule. Okay, add in the wavy line here to show where the molecule cuts. Okay, this is our secret, because a lot of people don't bother cutting it, and then they don't know how to draw the molecule later on, or they forget to cut something. Alright, so how do we check? C double bond O here, 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 and then the functional group. That's all. Okay, that's how we check for condensation polymers. Alright, same thing here, just going to show you how it looks like. So we cut here, we cut here, 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 and here, and you will get this. Simple as that. Next, show you the repeat unit again, and that's about it. Same thing, we're just repeating over and over again. Next one is terylene, which is polyester. I think you know the drill already. The only difference now is that we have diol. A diol, all means is your alcohol. So again, we do our cutting on both sides. Same thing, we cut here until we're left with the C double bond O. The other side we only cut and left one atom only. Okay, Same idea, you can take a closer look at it yourself. Alright, and make sure that you can check. You see, we have a C double bond O here, C double bond O here. Ending the C double bond O here, C double bond O here. Functional group, like that. Okay. Okay, so this is the repeat unit as similar to just now. Alright, and then just now as I mentioned, this thing, all these boxes are the unreactive groups. That means they are long carbon chain not reacting at all. So your job in the exam is to draw exactly whatever the exam give you the box. If they give you a shaded one, you just shade it. They give you a checkered one, you just draw back a checkered one, and so on. Okay. Okay, so your man-made fibers are just like this. Your man-made fibers are here. You just read the users yourselves. Usually your this all these things here, right, are usually your clothes, parachutes and all that, and plastics lah. Usually these are our main users. Okay, now we have a good question here, which is this terylene, which is talking about the sharp melting point. It does not have a sharp melting point, and what does this suggest? Okay, so I ask you to explain here. So melting point means we must talk about bonding and structure, right? Sharp means fixed, right? So like, what does this tell us? This tells us that it's not a pure substance, right? So it's a mixture, because polymer, you cannot guarantee that it's only one whole chain, right? There are many chains there. Okay, so the MR is different and size, so your intermolecular force of attraction is also different. So different parts and different amounts of energy will be required to melt the different parts. So that's why your terylene melts over a range of temperatures like that. Okay, so by and large, your polymers have giant molecular structures, strong covalent bonds between atoms. Okay, so we always talk about that. But if it's a range, because a giant molecular structure will not have a range, right? So if it's a range, then it's a simple molecular structure already. Talking about the different polymer chains, molecules already. Alright? Okay, the advantages and disadvantages can read on your own. And you can do these practices on your own. I'm just going to show you one example, the first one. So for example, if I have acid like this is what I expect to see from you in your answers. Like that, just draw it this way. Okay, cut the molecule, and then here, C double bond O, I must have a C double bond O, copy the chain like this. Then here is an O here, so I will put an O, C, H, and O. Here's an O, I must end with an O here like that. That's all. Okay, you can try on your own later on. Okay, and that's about it for your macromolecules already. Okay, that's all for today. Thank you very much.